I'll move from the very high level Chris was talking about back to the more micro level of individual behavior and looked at cybersecurity from the behavioral perspective, from trying to understand people. And if we, again, look at why things that are related to behavior may be relevant, we can have a look at this statistics that was published by IBM a few years ago that tried to identify the reasons why breaches occurred. And the first reason was misconfigured systems or applications, and the second reason was end-user error. So essentially we have 73%, 42 and 31% of events that happen because someone was doing they were not supposed to do. Someone screwed up. So people obviously are a weak link in cybersecurity, and we have to somehow figure out how we can create secure systems in spite of having people in them. We are trying desperately to get rid of them, but somehow it doesn't quite work. So the approach we take on, my group takes on this issue is the cognitive engineering approach, which is an interdisciplinary approach where we combine methods from experimental economics, mechanism design, sort of also theoretical microeconomics and experimental economics, cognitive psychology, obviously computer science, algorithm design, things like this, and mathematics optimization mainly. And we try to develop systems that are optimally suited to the situation in which we deploy them, considering the properties of the individual or the people who are using these systems. So the models then, obviously you have to deal with the system, the properties of the system, the properties of the individual user who used the system, and properties of the environment, and they have to be comprehensive in this sense. And they are an iterative process where we develop the model and we generate predictions, we run experiments or collect data in the field, and then we adjust the model accordingly, and then sometimes we actually succeed in changing something in the field based on these models. Now, basically, as everybody who has ever developed models knows, and as George Box says, all models are wrong, some are useful. So the claim that the models we developed are wrong is obviously correct, but it doesn't really matter. We know that this is true. The only question is whether we can actually do something with these models. So just to demonstrate this approach, I'll take a specific example. It deals with the security of large organizations, mainly infrastructure organizations such as utilities, companies, traffic regulation systems, and so on. In these places we have thousands of people having access to the systems, and the people are quite diverse in terms of their knowledge about the system, in terms of their risk-taking tendencies, in terms of the consequences risks may have for them, and so on. So one of the questions we wanted to address is, does it make sense to have individualized security privileges for different people according to some kind of properties that we may be able to identify for them? That's the basic question. So should, for instance, the utility company in Israel, the electricity company, decide for each employee what exactly their privileges are? Can someone do more or less than someone else based on people being more or less cautious and so on? And so these are actually three questions. What are relevant differences between users? The relevant differences according to which we want to perhaps adjust the system. What are the optimal security settings for the different users? And in the security settings, I mean something very specific. Actually, there are two different ways in which a system can interact with the user. One is provide the user with information, usually in the form of alerts, and then the question is, what do I alert about and what's the alerting threshold? And the second option is that it simply block for certain actions from the user. And the question is, what actions do I block, and what, again, is the threshold by which I block the system? And then individualized security settings means that different users have different alerting systems settings and different blocking settings. And the third question is, what are the behavioral responses to specific security settings? And we know of a number of security behavioral aspects that are relevant here. For instance, the cry-wolf effect, which is probably familiar, or alarm fatigue, where if I issue a lot of alerts that tell you that the site you're trying to access it doesn't have a valid certificate or is problematic or so on, the browser alerts we see here, then people simply learn to ignore these issues, these alerts. Or another problem that maybe is the reactance. If I block someone, then after a while, the person may get some upset by the fact that I'm blocking her or him, and then consequently will try to circumvent the blocking and do things I've tried to prevent in spite of my blocking. So we developed some mathematical models of this. I won't go into the details. It's sort of a mixture of different methods. We do some analytical work, we do some numerical analysis, and we do some Monte Carlo simulations and try to figure out what the optimal system is in different situations. Basically, the scenario we look at is a scenario where someone downloads some web components, for instance, for a software project, and the component may be malicious or not. And there's a price, there's private information, the component can be malicious or not, and so on. One of the tools we use is signal detection theory, which is a mathematical theory. It's essentially a decision theory where we have two different states of the world, signal and noise, and we have the difference between the means of these two states, which is the sensitivity of the system, and we have a threshold which determines which events are categorized as signal and which are categorized as noise. And basically we model the situation in which we have some kind of information that gets from a website or component through the alerting system as an alerting output. We get some additional information through the cost that is issued by this website, and we have some private information, and this is then somehow combined, and the decision is made whether to access the site. So we can model this. Basically, it's an individual decision-making problem. We don't model this as a game theoretical problem, although this is also possible. So we don't assume that the attacker adjusts their behavior according to our responses, but that's the second level of modeling we start to look at now. And we can look at responses to warnings and to blocking. And it's essentially an expected value calculations, which allow us then to define some kind of thresholds at which we, for instance, buy a component, even if there's a warning, buy if there's no warning, or don't buy, as a function of the cost of this component and of the private information I have just in this example. So just some of the results we get from these analyses, just to demonstrate the general approach and what we get. If we have, one of the questions we ask is, let's assume that we have an alerting system. We can have a binary alerting system where they actually either get an alarm or don't get an alarm, or we can have a likelihood alarm system where we have multiple levels of alarm. And if we compare the two, then the mathematics shows that we get higher payoffs with the likelihood alarm system. And if we compare blocking versus warnings, we can show that very easily, it's very easy to prove that you will always have higher payoffs with warnings than with blocking, or have the same, but you will never have better payoff with blocking than with warnings. And in terms of the number of security events, we can show that there are more events with the binary alarm system than with the likelihood alarm system, and fewer events with blocking than with warnings. Now, as I said, there may be a difference between what actually people do and what we measure in our, or what we compute in our mathematical models. So we ran some experiments. It's essentially a very abstract simulation of these decisions. We show people sort of a task in which they select or do not select an information source, sort of a component, have some private information that tells them what they know about this information source. We manipulate the information they get. They have some indication about the cost. In some experiments, in others, we don't show this. And then they get an indication that says, please download, or they are blocked, or they get some warning, one of two different types of warnings. So we try to simulate the situation that we capture in the mathematical model. And then they get some outcome, and we pay them according to the outcome, so they are somehow motivated to do good in this task. It pays off for them. And if we compare the results in the experiment to the predictions of the mathematical model, we see that with binary alarms and likelihood alarms, there's indeed a slightly higher payoff with likelihood alarms as predicted by the mathematical models. In terms of the blocking versus warnings, there's no significant difference. And when we look at the security events, there's no significant difference between binary alarms and likelihood alarms, in contrast to what the model predicted. And there are indeed fewer security events with blocking than with warnings. So what we get is that sometimes the model predicts what's happening, sometimes it doesn't. So if we look at the overall picture, blocking leads to fewer security events. There's no significant difference in productivity and total payoff between blocking and warning, so we see that although the mathematical model predicts that blocking will always be inferior, we don't find this in the experiments. And in general, model predictions have some descriptive value. It makes sense to develop mathematical models, so they allow us to generate some predictions of what's going to happen, but predictions need to be tested versus empirical data, and there are conditions in which actually the empirical data differ systematically from what the models predict. So what we need is a model and a mathematical models that takes into account these differences and sort of adjusts to behavioral regularities that are not necessarily exactly in line with what we would predict for a perfectly rational decision making. So that's basically the approach we try to push here, and we're doing this in a number of different contexts, including, for instance, authentication, which has been talked about earlier today, alerting systems, privacy in different contexts, and so on. So I think I'll stop here, and thank you very much. Question. Otherwise, actually, Yaniv asked to perhaps end this session a little bit earlier because the next session has 5 speakers and we want to have a little bit more time for that. So if there's a question, I'll be happy, and otherwise we can move on to the next session. Chris, did you? Oh, yeah. Sorry. So we look at this, there are 2 different levels at which we look at this. At one level, we look at individual difference in risk-taking tendencies, and we can show that there are systematic individual differences. Actually, it's a different line of research we do, but it turns out that different people take different types of risks. So we identify at least 3 different behaviors that are related to risk-taking in the cyber context, and different people tend to be sort of the risk-taking in different aspects, and you can predict this. You can predict this with standard measures of risk-taking in different concepts. So there are individual differences, and there's obviously very strong situational determinants. So people take greater risks when, for instance, when they're under time stress, they take greater risks in situations in which they feel that they know exactly what's going on. Even though if they don't, they may not know this, but they feel this is familiar, then they may take greater risks and so on. So it's a very interesting question. Okay, thank you. Yes, please. Yes, please. Yeah, so yeah, that's absolutely true. The question was whether we can model the possible effects of fatigue on risk-taking, and I think this is a very, very important issue if you look at risk-taking in actual real-life situations. So we do some research. We have done some research on the effects of boredom and fatigue on decision-making, and it turns out that they have very strong effects indeed. It's not easy to do this in an experiment, and you all have to deal with problems of ethical conduct towards participants, because having people do 2 or 3 hours something terribly boring can be really cruel. But it's obviously a very interesting, very important thing. We can model this to some extent if we assume that the that some of the parameters of the mathematical model change. For instance, the D prime, the ability to distinguish or the setting of the threshold and so on. That's important. Okay, thank you very much.